Okay, so now we are going to look at a very simple model of an electron in an atom. And this simple model is going to be, well, it's going to be on the one hand simple enough that we're going to be able to analyze it completely and understand exactly what states are allowed and so on. But on the other hand, it turns out to be a surprisingly good model for the allowable states of an electron in an atom, and therefore it'll help us understand very concretely what an atomic qubit might look like. Okay, so here's what that model is. It's called a particle in a box, and you can think of it as a toy model for a hydrogen atom, where the electron is confined in the vicinity of the proton by Coulomb attraction. So you can think of, to a first approximation, you can think of this electron as trapped within a box. It's a pretty tiny box. It's about 1 angstrom in length, or roughly 10 to the minus 10 meters. And so, of course, Coulomb attraction is, it's more complicated because it falls off with the square of the distance. But to first approximation, we'll think of the electron as just confined in a box with hard, in this spherical box with hard boundaries. And so we can think of this, even though it's a three-dimensional picture, as a one-dimensional picture, because the only variable is how far you are from the center. And so this is our model for the electron. It's confined to a box of length L, and then it's a free particle within this as long as it stays in the box. But then it's not allowed to step outside the box because of an infinite potential outside, which makes its effective energy infinite as soon as it steps outside the box. And of course, this little electron just doesn't have that kind of energy, so it's disallowed from being anywhere outside. Okay, so how are we going to figure out what the state of this electron is? Well, we'll solve Schrödinger's equation. What's Schrödinger's equations? IH bar d psi by dt equal to h psi. But what is h? What's the Hamiltonian in this case? Well, since we have a free particle, as long as we're outside of this, as long as we stay in the box, it's p hat squared over 2m psi plus Vx, where Vx is the potential energy. And so, for a free particle, this p squared over 2m, of course, ends up being minus h bar squared over 2m d squared by dx squared. And the fact that psi x, we have a non-zero potential, we can just translate into boundary conditions which say that psi of 0 equal to psi of L equal to 0. Okay, so now what we are left with is the question of, now that we know what the Hamiltonian is, we are left with the problem of solving Schrödinger's equation for this given Hamiltonian H. Now remember how we solve Schrödinger's equation. Well, it looked daunting to us, and then we said the way to solve it is to first solve for the eigenstates of H, because those behave very nicely under Schrödinger's equation. So what we first do, so here's an outline of what we do. We first solve H times phi equal to lambda times phi. And once we find such an eigenstate, then we know that if psi at time 0 equal to phi, then psi at time t is e to the minus I lambda t by h bar phi. Okay, so all we need to do is figure out all the eigenvectors of H and all the eigenvalues, the corresponding eigenvalues. And then, as long as we take the initial state psi and decompose it into the eigenstates of H, we can understand how that state will evolve, because essentially each eigenstate is almost invariant. It just, you know, it just marches to its own drummer, which is its eigenvalue, and it does so by this phase precession, e to the minus I lambda t over H bar. Okay, so what are the eigenstates of H? Well, let's guess that the eigenstates of this operator, we have H, that H equal to minus H bar squared over 2m d squared by dx squared has an eigenstate of the form phi of x equal to e to the I kx. Okay, so now if we apply H to phi of x is minus H bar squared over 2m d squared by dx squared of e to the I kx, which is H bar squared over 2m k squared e to the I kx, right? Because you get an ik whole squared when you take the second derivative, and I squared is minus 1, so that cancels this minus 1. Okay, so this is an eigenstate with eigenvalue e equal to H bar squared k squared over 2m. Okay, and of course we have the same eigenvalue for e to the ikx as we do for e to the minus ikx, and therefore we have an eigenspace, and so our solution is going to be of the form phi sub e of x is a times e to the ikx plus b times e to the minus ikx. This is all of these, for every a and b, this is an eigenstate of this operator H with eigenvalue e sub k equal to H bar squared k squared over 2m. Now of course we are not yet done, because we have to impose the boundary conditions that phi at 0 must be equal to 0 and phi at L must be equal to 0. So it turns out that it's convenient for us, if you remember, e to the I kx is cosine kx plus I sine kx, and similarly e to the minus I kx is cosine kx minus I sine kx. And so instead of writing this in terms of e to the ikx and e to the minus ikx, we could also write this down as a linear combination of sine kx plus d cosine kx. Okay, so let's see. So where are we now? What this leaves us with is we have phi sub e of x is c sine kx plus d cosine kx, and this has energy E sub k equal to h bar squared k squared divided by 2m. Now we have to impose two conditions. We have phi of 0 must be equal to 0. So at 0 sine kx equal to 0, and this is equal to c times 0 plus d times 1 So that already tells us that D equal to 0. Okay, and then we can impose the second condition that phi of L equal to 1. So phi sub E of L equal to 0, which means that C times sine K times L equal to 0. So this tells us that K times L equal to n pi, where n is an integer. And therefore we get K, which is a function of n, is n pi divided by L. And so this gives us our quantized function. So the energy eigenfunctions are E sub n is h bar squared K sub n squared over 2m, which is h bar squared n squared pi squared over 2m. Okay, so n just takes on integral values 1, 2, 3, and so on. And what do our eigenfunctions look like? Well, phi sub n of x is just c times sine kx, which is k sub nx, which is n pi over L times x. Okay, so are we quite done? Well, not quite, because we must normalize. We must normalize to make sure that the integral of this from 0 to L is 1. The squared. So let's set this up. So finally for we must have integral from 0 to L of c squared sine squared n pi by L x dx equal to 1. And of course, if you add in cosine squared to this, you would get the integral is c squared L, and that's 2. So c squared must be 2 over L, which implies c squared equal to 2 over L, or c equal to square root 2 over L. Right, so it's this, you can replace this c by square root 2 over L, so the wave function is square root 2 over L times this, and that's the energy. So here's our solution then. So the solution is, that's the energy, so our solution is quantized for integer values, that's the energy, and that's the corresponding wave function, right, for n equal to 1, 2, and so on. And if you plot it out, then when you have n equal to 1, you have sine of pi x over L, which goes like this. It starts at 0, etc. When n equal to 2, you get a full cycle of the sine wave. When n equal to 3, you get 3/2 of a cycle, and so on. And so our wave function is quantized, right? These are eigenstates, right? These are the eigenstates of H. These are the wave functions with definite energy. And what's the energy? Well, that's the corresponding energy, right? So these wave functions have an increasing energy, increasing like proportional to n squared, so 1, 4, 9, etc. And these particular eigenstates are like standing waves, right? Okay, and of course, if you're given any particular arbitrary psi of x, you would decompose it. You would write it as alpha sub n psi sub n of x. And so if this was psi sub x at time 0, then psi of x at time t would just be alpha sub n e to the minus I e sub n t over h bar psi n of x.